I'd like to give a short overview of what I mean by a linear function. And most of the time we think of linear function, we want to try to think about something from geometry. We want to say, oh, if something is a line or something that is a plane, then it's a linear function. And in one sense, it is a plane, it's a line, so there is some truth to that point. But at the same point, it's not quite the way we define linearity. And linearity has a very specific definition because it gives us very particular properties independent of the functions being used, whether it's a line or not. And so this is where we begin. And what happens is what we find is this very straightforward definition of linear function where if I have a function, we'll call it f of some argument, and I multiply something inside it by a constant, a, that constant just comes out. Or if I have another value, f of y, and then I multiply it by b, it just comes out. And it also has the property that if I add the two, it is basically the separation of those two. Now that feels like a line, but a normal line also often has an offset, and that offset actually throws you off here. But there's a whole range of functions that are linear. And there's some very important aspects of why this matters. But let me give you a couple, and by the way, that's also true if I take the function of a function, you'll get the same conversation here. So you obviously know as a basic, a simple gain factor may feel like a linear thing. But it also turns out the operations of differentiation and integration, for those who've done calculus, realize that those are exactly linear functions because, in fact, if there's a constant, it comes outside of the derivative. If there's something that's added, then I can do each part separately. The same thing is true for integration in the same way, being the inverse operation. So differentiation and integration are linear operators on a situation, on a particular function or something to be operated on. You do get this sort of very simple gain factor, which gives you the sense of the simple part of this. Imagine I just have a gain times a function. That gain comes out either in integration or in differentiation. Excellent sort of property. We're really glad this is the case for a whole range of things that we do. And what's really interesting is that linear, particularly time-independent systems, are typically characterized by sinusoids and exponentials. And in fact, particularly if it's a time-independent system, really interesting property. I put it as single frequency input. And time-independent, for those who aren't familiar, basically means that it doesn't matter where you start. And that usually precludes having all sort of the time-varying inputs and so forth. But if I have a sinusoid going to the input of that linear system, my output may have a different amplitude and a different phase, but it will have a frequency and only that frequency out of it. And this turns out to give us some really interesting opportunities for these linear time-independent systems and a way to characterize and approach this. And that specialness is something we use a lot, particularly if, let's say, I want to make a filter, but I want to preserve all of the things that I don't want to get rid of. I want to make sure it's preserved well. Well, that linearity will matter. In many other functional cases, that linearity matters. So there's a very important property for so many different cases.